Hey, welcome physics to the second flipped class lecture here in chapter 2 now of our physics book. We're going very quickly through chapters 1 and 2 because, well, you've had all of this before. This chapter will be in its entirety something you've had in chemistry and also in physical science and certain aspects of it in biology as well, although less there. As always, I'm going to just take as long on each slide as it takes to explain it. So if you need to pause the video to copy down any of the notes, you are at liberty to do so, and that would be recommended. Also, if you have any questions from this lecture, please use the comments field below on the blog page, and I'll respond as quickly as I can to that. We'll either cover it on the blog or I'll address it when I see you in class. So here we are, reviewing of measurement and accuracy, chapter 2 in a flash. We need to remember some things about the physical world that you've covered a little bit in geometry, a little bit in physical science. When we talk about dimensions, we talk about, we live in a world of 3 dimensions, right? Height, width, and depth. And what does that mean? Well, let's build them slowly. So a point, and if you remember that term from geometry, is a location that has no dimension. So it has no height, width, or depth. It's just a location. If you have 2 points, you can connect them with a line, and now you have defined 1 dimension. A line goes left or right forever, but it has no up or down or back and forth, right? So a line has 1 dimension, and then if you have 2 lines that intersect, you can create a plane which has 2 dimensions, like a piece of paper or a bed sheet or a curtain. This has 2 dimensions. It goes left and right and up and down, but does not have any depth. In order to get depth, you have to have a plane and a point to define space. And that is the world that we live in. Physics will often operate in either 1, 2, or 3 dimensions. Very frequently, the problems that we'll be doing, I will say, assume 1 dimension, where I only care about how far apart these 2 things are from each other. I don't care about anything else around them. Or I might say assume 2 dimensions for something like parabolic flight. You launch a cannonball, and I care how far up it goes, and I care how far out it goes, but I don't care about left and right. Or we might actually care about all 3 dimensions. When we're talking about collisions, very often it is 3-dimensional. So sometimes it's 1 dimension, sometimes 2, sometimes 3. You just need to be familiar with what those terms mean. There is a 4th dimension, and that is time. So time is the 4th dimension. So I'm currently sitting here on my chair in my room, and you could describe my location with height, width, and depth. But you could also say that I'm sitting on this chair at a particular moment in time. So if you were at the same location tonight at 1 in the morning, I'm not going to be here. And that's because, according to the 4th dimension, I'm not here then. Time has taken me somewhere else. So there are 4 dimensions, and we only experience time in kind of like half a dimension. We go one way in time. We can't go backwards in time. And so physics hasn't figured that out yet, at least. So some pictures to help you with that. We have here the concepts of a single point without space with this point D here on the field. And then, so this has no dimensions, it's just a location. But if you have a couple of different points, at least 2 of them, you can define a line, which now this has 1 dimension. It goes back and forth in every direction one way. If you have 2 lines, like this line here and this line here, then you have, you've defined 2 dimensions, you have a plane, right? And now plane and a point outside it, or in this case they've just drawn another plane, helps you visualize space. So now you have left and right, up and down, back and forth, okay? You can also picture it this way, as 3 dimensions. Often we talk about the x-axis and the y-axis and the z-axis. And so actually I pointed those out the wrong direction, didn't I? But you get the picture. The x-axis is horizontal, the y-axis is vertical, and the z-axis is in and out of the page. So this helps us picture something in 3 dimensions. And then remember that time is a 4th dimension, but it only goes 1 direction. So we only experience time in one way. We can't go backwards. Alrighty. So When we get into physics, the first unit that we're going to get into is classical motion, studying the movement of things according to Newton's laws. And much of physics, even things that are not just classical mechanics, are going to be loosely defined as matter in motion. And so we need to define what matter is. Matter is anything that has mass and takes up space. So you matter, congratulations, and so do I. And so does this cell phone, although less so every year. But anyway, anything that has matter and takes up space is, anything that has mass and takes up space is matter. So what does it mean that it has mass? Well, we commonly think of how much mass something has when we weigh it. So I have a certain weight, and you could express my weight in kilograms, which is the unit of mass, and you might think that that means that mass is something that weighs something. Well, in an area that has gravity, that's experiencing a gravitational field, you can measure mass with weight. But in the middle of space, floating around out in the cold vacuum of nothing, I would still have mass, even though there would be no way for you to weigh me. So mass is actually better defined as the ability of an object to resist a change in its direction. So if I'm hurtling along at 20 miles an hour in some vehicle carrying me that way, and you then try to change my direction, because I have mass, my inertia is going to want to carry itself forward in the same direction, and I'm going to resist that change in mass, in direction, because of my mass. There you go. And that definition works even without gravity acting on it. So that's independent of gravity. That's a better definition of mass than some kind of weight measurement. Okay, so keep that in mind as we're talking about mass. And that leads us into some standard measurements. We use the metric system here. The rest of the world, except America, does as well. So we do in the sciences. We're going to be using units like the meter, the liter, the gram, etc. I just said 20 miles an hour a few seconds ago. That would not have been appropriate. I should have said something like kilometers an hour, but I think you forgive me. So in science and every other place in the world, besides common American supermarkets, we deal with the metric system. So if you need to look at those units again, they are described in Chapter 2 of your book. We also need to remind ourselves of bridge notation. Oh, grumble, I know. You hated it, but it's still with you. So bridge notation helps us convert units. And so in this example here, if I wanted to know how many milliliters are in 14 kilograms of water, I would start with my 14 kilograms of water, and then I would say, hey, look, in every 1 kilogram, there are 1,000 grams. And the density of water is 1 gram per milliliter. Okay, so I could say, well, that's really convenient. 14 kilograms times 1,000 grams per kilogram times 1 milliliter per gram. All of the units cancel out, kilogram, kilogram, gram, gram. And I'm left, the only unit I'm left with is milliliters. And I multiply across 14 times 1,000 times 1. And then I multiply across in my denominator, 1 times 1. So 14,000 divided by 1 is 14,000. There would be 14,000 milliliters in 14 kilograms of water. That's a very simple expression or a very simple example, but you understand the point. We did this a ton in chemistry. It is still with you. You still need to know how to do it, okay? There is some review in Chapter 2 if you need help with that, or feel free to stop me anytime during class and I'll help you with it, okay? We've also talked about accuracy and precision before. Accuracy is how much your measurement relates to reality. Does it correspond to reality? If you say Mr. Alley weighs, I'm going to pick a number, 100 kilograms. Let's just make that a round number. That's about right. If I weighed 100 kilograms, or you say I weigh 100 kilograms, but in truth I weighed 101.674 kilograms, well, you're not quite accurate. You're off by a little bit. But if you were to say I weighed 100 kilograms and in truth I weighed 120, oh gee, I hope not, kilograms, 120 kilograms versus 100 kilograms, that's off by a lot. Your accuracy is poor. So accuracy is the degree to which your measurement corresponds to reality, okay? Precision is used actually in two senses in physics. In chemistry, we talked about precision with regard to how repeatable is your measurement. If you take the same measurement 48 times and you get the same answer 48 times, that's highly precise. If you measure the same thing 48 times and you get 25 different answers, you got a problem with precision. So precision is the repeatability of a measurement. It's also how many decimal places or how many significant digits you've measured to. So I'll show you an example of that in the slide that follows. If you have a tool that measures just a couple of significant digits versus a tool that measures a lot of significant digits, you want to get the better tool that measures a greater number of significant digits because it's more precise. Okay? And then when you are reading a measuring tool, be it a meter stick or a graduated cylinder or a scale, whatever measuring tool you have, you always want to read as many significant digits as it gives you. And then, if it's an analog scale, you want to infer or estimate another decimal place. So if I'm reading a scale and I put my little slider over and the scale itself reads 3.2 grams, but the slider is not quite on 3.2, it's a little closer to 3.3, but it's not, it's not more than halfway to 3.3. I might say it's 3.24 or something like that. So you always want to estimate the last decimal place that you can. Now, if it's a digital scale, you can't estimate because you don't have a pointer on a scale to read. If it's a digital scale and it says 3.24, then you write down 3.24. But you always want to capture as many significant digits as you possibly can. Okay, just some pictures to help with these ideas. Accuracy is being close to the target, being the right number, being corresponding to reality, okay? Precision is having a lot of measurements close to each other. It's highly repeated. So this measurement is accurate and precise. This measurement is not accurate. The measurements are not in the field, right? But it is precise. They've been repeated many times. This picture is neither accurate nor precise. They're kind of all scattered all over the place, and they're not around the bullseye. Okay, it's not actually what it is, and they don't agree with each other. This is an example of accurate measurements. Several of them were correct, several of them were close, but it's not precise because they're all scattered all over the place. Okay, precision is repeatability. Accuracy is how much your measurement corresponds to reality. Two examples of scales here. You have a spring scale, which would only read just to maybe a tenth of a gram at its best. And then you have an analytical scale that will read out 200,000ths place of a gram. So these are just examples of two different tools that do the same thing, but one is a lot more precise. It reports more significant digits than the other. Okay? So we should review significant digits. So the rules for them are on page 36 of your book. If you need to review significant digit rules, go there. The nutshell is that if you're looking at significant digits, it's the zeros that matter. Leading zeros never count. Trailing zeros count if there's a decimal place. Okay, that's just the quick nutshell picture of significant digits. Your answer should only have as many significant digits as your least precise measurement. So make sure that you are always honest in your math, that you don't report more significant digits than you actually measured. Okay. Also remember to only round in your final answer. Do not round along the way. We want to avoid as much error as possible. And scientific notation is your friend. If you have a really big number and you can only express 3 significant digits, then express it as a decimal number raised to the power of 10. Okay? So we did a lot of that. That is your friend. Remember how to use that. And then lastly, mathematics and physics. You are going to be doing a ton of math and physics. So don't be afraid. Just get used to it, roll up your sleeves, and do some math, okay? You will always get the equations handed to you. I will never expect you to memorize an equation. Memorize how to use the equation, not the equation itself. You will always have the equation to reference. And then always remember to go back and check your answer for reasonableness. Does your answer make sense? If you say that a chicken weighs 98 kilograms, you're probably wrong. So make sure that, that your answers always make sense, and that'll help you not make silly errors. So there you go. Chapter 2 in a whirlwind. Pause if you need to. Ask me questions later. Have a great evening. God bless you.